Hi everyone, I'm Pranav Kulkarni and I work on the ArcGIS Hub team at the R&D Center in Washington DC. And today I will be talking about how we build a scalable and a reliable web backend system using microservices. Before I delve into any of the technology and its details, I want to quickly talk about the ArcGIS Hub product. ArcGIS Hub is an engagement platform that allows government and citizens to connect with each other. It's a platform through which you can manage people, process, and technology. Through initiatives, the ArcGIS Hub enables governments to share information with citizens, collaborate with them, and also monitor progress towards its goals. ArcGIS Hub has actually evolved from this other product called ArcGIS Opendata. It's a platform where one can share authoritative open data, and also you can set up public-facing websites through which you can download such open data. The backbone of open data is basically a data harvesting system that collects metadata about these data sets from various ArcGIS online servers and puts them into like one big data set. So there were a few problems that began to creep up with the ArcGIS Opendata. First of all, it was a huge monolithic architecture built using Ruby on Rails. And this Ruby on Rails app had to do too many functionalities like routing, data harvesting, search index, data persistence, etc. There was a lot of tight coupling between various components of the app, which made development really hard and also slowed down release cycles. There was no continuous deployment, but there was continuous integration using Travis. We also used to do manual releases through AWS OpsWorks, which was not that great. And then the app and the infrastructure were not designed to run in containers, and hence the system as a whole was not scalable. Many a times engineers had to intervene to actually scale instances in production. Lack of log management and monitoring resulted in a waste of countless hours in debugging. So we decided to build the next generation of the Hub backend system to address all those problems. We identified the core features of our product, that is data harvesting, improving search and discovery, and scalability. So we decided to break down the system into small individual components where one component had mainly one functionality, and we wanted ease of maintenance, and also we wanted a quick turnaround time in development, which meant that multiple developers could work on the same repo on different components simultaneously, and we wanted a system that was quickly adaptive to change. And of course, we wanted to build some confidence in our apps with continuous integration and deployment. So microservices came to our rescue. This is the basic architecture diagram of our Hub backend system. When an item is created and published in ArcGIS Online, a notification is created which is put onto a Amazon SQS queue. Now all the boxes in this diagram are actually microservices running in their own containers. The listener picks up that notification from Amazon SQS queue. The message contains an item ID and some metadata about the item. The listener, also known as the scheduler, then tries to schedule a job. A job is a basic unit of work that needs to be done on the item and stored in our own Elasticsearch index. So this job is basically a JSON structure that we store in a jobs database. Now this jobs database is a relational database because of its resiliency. The dispatcher regularly polls for jobs, and it removes jobs that are scheduled to be run at any given point in time, and it puts those jobs onto a message broker, which is RabbitMQ. There are two queues, the request and the response queue. the messages on the request queue are meant to be executed immediately by the worker. Now let's quickly take a look at how the job worker system really works. So we have a very consistent set of instructions, a JSON document that you can see. It consists of the item ID, the job type, and the job name that needs to be run. In this case, we are trying to compose an item from ArcGIS Online. So all the jobs basically have this signature, like the read instructions, the execute, and the update index. In general, the execute function either creates a new document or fetches the existing document from Elasticsearch, makes some modifications to it by adding some information or doing some new calculations and adding stuff back to that document. And the third step is to update the Elasticsearch index by pushing those changes back to the Elasticsearch as the data store. So since this is the first step, which is the compose step, here the item is first fetched from ArcGIS Online store. We also fetch some other information like layers, server information, formal metadata, etc. And with some basic calculation and everything, we just compose all these components into one JSON document. And the worker then executes the update index on that same job module so that the new changes are persisted in Elasticsearch. So once the job is complete, the worker places a message onto the response queue. The scheduler which subscribes to the response queue gets notified that the composed job is now completed, and then it takes the next set of actions. So the scheduler can then schedule a few more jobs for that composed item, like validations and enrichments. Validations are some basic set of jobs which basically test whether an item has like proper data format and just make sure that the data is not corrupted. It can also schedule enrichments. Enrichments are some new kind of jobs that add more value or information to the data set, like adding semantic tags using some machine learning technique or calculating the extent of the item. So these enrichments improve user experience by adding more value and information to the data set. Let's just quickly look at how the enrich job looks like. So the enrich job and even the validation jobs, they all like look pretty similar. They have the same signature. Because they have the same signature, it makes it a breeze to like add more jobs to this entire system. Okay, so many times the workers have to like talk to external services which may be outside the cluster, and we may want to like rate limit some of the requests. That's why we have the Nginx worker proxy to do that rate limiting. So in this entire workflow, whenever a job fails, the scheduler tries to reschedule that job with the job instruction, the retries field. We have, at the end of the workflow, there will be one data set in the Elasticsearch that will be made available to the clients through an API. The primary focus of the API, which is a Node.js Express server, is to filter and search data sets and serve the clients. It was actually obvious to run these microservices in different containers, and Docker out there is the most popular container technology. Now, interesting part here is that we have all these microservices in one repo. That is, they share code amongst each other. That means there is only a single Docker image. We use this concept where each container takes a role. What that means is there is a shell script called Docker entry point. It spins up multiple containers from the same Docker image and starts a process in each of those containers. Like the Docker entry point will spin up a container and start the worker process in it. It will spin up another container and start scheduler in it, and so on. So the biggest advantage is that it reduces the overhead of maintaining multiple Docker images, and by sharing code, we also reduce the number of HTTP calls or message passing between these containers. So with the use of container technology, we had to decide on how do we manage these containers. That's where we chose Kubernetes, which is a container orchestration technology. It has many advantages, like Kubernetes is a declarative configuration and provides automation out of the box. It provides other advantages like auto scaling, and you can do your own deployments. And there's an easy to use API for the Kubernetes cluster. So each service in our repo actually gets deployed as a deployment in Kubernetes terminology. It is basically a YAML file, as you can see there. So in the YAML file, you specify like the namespace, which is the logical area in a cluster where you want to deploy the container or a pod. A pod is just like a collection of containers that are like related to each other. Like we will have a pod for each microservice in this case. You can also specify the environment variables and the resources as to like how much this particular pod should actually take. The interesting point here is to note that we build all the microservices from the same Docker image, and we also provide the command, that is the Docker entry point that I just talked about in my previous slide, and which process needs to run in that container. Kubernetes provides horizontal pod autoscaler, which is basically used for autoscaling. Autoscaling is currently done based on the CPU usage. So when the CPU hits a certain threshold, a new pod or a new container is actually spun up automatically. There are terms like min replicas and max replicas, which basically tell the cluster as to how many pods should be running at least at a given point in time, or at most at a given point in time. So with the use of Kubernetes, the container technology and microservices, we were able to separate out the concerns for dev and ops. Continuous integration and deployment was really an icing on the cake when we were deploying this hub backend system. Jenkins provides a declarative configuration for automating most of the processes. We have Git hooks configured in our repo. On every commit to a PR, a Jenkins job runs, and when we actually merge that PR into the master branch, the Jenkins pipeline kicks in, which does the following things. It first runs the unit tests, does some basic linting. It builds the Docker image from the repo and pushes that Docker image to AWS ECR repository. And it also creates the deployment YAML files that I showed you in the previous slide. So in order to deploy the application, we have created a separate command line tool in Node.js. We call it the kubeutil, which we have open sourced, by the way. So this command line tool actually sticks in the configuration parameters for various environments like dev, QA, and prod in those templates and deploys the application onto the cluster. So once the deployment is successful and on dev and QA cluster, we run end-to-end tests on those clusters, and if they are successful, the pipeline automatically deploys the new code to the prod cluster. Once this whole pipeline gets completed, we get notified on Slack, and if at any stage the deployment fails or the end-to-end tests fail, then the whole deployment gets rolled back automatically. I'm going to talk a little bit about the Kubernetes cluster. We've set up the Kubernetes cluster on AWS using a command line tool, of which the kubeutil was a spin-off. So this command line tool, as you can see in the top right corner over there, it provides multiple functions like create a new cluster, destroy the cluster, or create a hosted zone, and so on. So in the creation of a Kubernetes cluster, there are many steps that are very interconnected with each other. So we decided to create a Node.js command line tool, leveraging the kubectl and the kops commands that come with Kubernetes. So kops command is basically used to create a cluster, and kubectl is used to configure the cluster. So creating a cluster involves basically deploying this YAML file. In the YAML file, you can specify things like where should this cluster be created, what is the VPC ID, and which IP addresses should have access to the cluster, and what's the name of the cluster, and so on. So the biggest advantage of actually creating this command line tool was that we can create a Kubernetes cluster in any AWS region we want, and this whole process is repeatable. We totally treat infrastructure as code, which means we have all the configuration YAML files and the command line tool in one repo. So in this repo, there are actually two pipelines, two Jenkins pipelines. One is to build the cluster, and the other is to apply updates to a cluster as if it were an app. So let's focus on the build cluster pipeline. So the build cluster pipeline is a Jenkins Groovy pipeline. It uses the command line tool that I mentioned just before. It creates a cluster, like provisions the EC2 resources, and does like simple configuration, like who should have access to it and the IP addresses and all those things. Once the cluster is created, it also creates the namespaces. A namespace is a logical area where you can deploy a similar set of deployments or pods. It also installs a monitoring system like Prometheus and some log management tools like Elasticsearch and Kibana. And once the deployment is successful, it also deploys the apps. So let's say the cluster is ready and the apps are deployed on it, and we may want to apply some updates or make some changes to the cluster, but we don't want to create a new cluster. That's where the CI/CD pipeline is actually useful. So whenever we want to make any changes to the cluster, we check those changes into the master branch in the repo, and those changes are first applied on the dev and QA cluster, and we run the end-to-end tests of the applications that are running on the cluster as regression. Once they are successful, then those same cluster changes are applied on prod. So one might actually wonder, like, things like monitoring, log management, alerting mechanisms will be really difficult with, such a distributed architecture of microservices. So the solution is to deploy a monitoring system also as a microservice. So we use Prometheus for monitoring. Prometheus provides a time series data model identified by metric name and some key value pairs. It has some other advantages because it comes with a declarative query language, and it provides alert manager out of the box, which integrates with other third-party apps like Slack and PagerDuty. So we've deployed Prometheus in a separate namespace from the namespace where the apps are running. Prometheus scrapes data from different pods and deployments, which may be running on different nodes. And once it collects all this data, it runs its own calculations and does some just calculates some metrics which we have predefined. And if any of those metrics cross a certain threshold, we get notified on Slack or PagerDuty. So here's one example of the Prometheus monitoring. In the upper left corner, it's monitoring the API pod. So it's actually monitoring all the endpoints running on API. So whenever, let's say, the request latency goes over a certain threshold, then we get notified on Slack with very specific details as to what was the endpoint of the API that created this event, or what's the pod name, what's the node name that actually created this event, and so on. Similarly, here we have monitoring on RabbitMQ. As to like how many messages there are on RabbitMQ, and if there is if it crosses a certain threshold, we get a similar notification, which probably means that the workers are not processing RabbitMQ messages fast enough. So for log management, we use a combination of Fluentd, Elasticsearch, and Kibana. Fluentd is a data collection app. It collects logs from various containers and enriches those logs by adding some metadata like Kubernetes pod name, node name, container ID, and timestamp, and so on. It basically collects all those data and puts it into an Elasticsearch log store. And we use Kibana as a visualization tool to view the logs. So here we can actually check the logs of all the scheduler instances by just specifying that get me the logs of scheduler. So this basically makes the developer's life easy by able to look into logs from multiple sources. So what did we learn? We learned that breaking down a system into small individual manageable components is the key, and microservices help us achieve that. And investing a good amount of time and energy in microservices, container technology, and CI/CD ultimately reaps benefits like increase in developer productivity, and you will know that your apps will scale well and perform really well. I think that's it. If you have any questions, please let me know. Yeah.
I'm not sure if you covered this, but how do you get a notification out of ArcGIS Online? There are no webhooks there, right?
No. So, okay, the question was how do we get notifications from ArcGIS Online? So we have a Amazon SQSQ. ArcGIS Online actually publishes that message to Amazon SQSQ, which the hub indexer, the backend system, the listener component is listening to that Amazon SQSQ. Yeah. Any other questions? Okay, cool. Thank you all for attending.